Yes, hello and welcome student to this class, and this is course number MA412 linear algebra. um, algebra this is lecture number 26. Okay, now recall in our last lecture we discussed about Gram-Schmidt method. Okay, Gram-Schmidt orthogonalization process, right, that we discussed. And this method tells you that given a linear independent set, finite linear independent set, you can make another orthogonal set such that both the set they span the same space, right, same subspace of the original vector space, right. And the immediate corollary was what, that you can immediately say that if you be say for example vector space or inner product space with dimension finite, and suppose we then obviously then we has an orthogonal basis, orthonormal basis. Okay, say B, and you can write down the vector like for example n, where dimension of v equal to n. Okay, and not only that, the interesting thing is that for any v belongs to small v belongs to capital V, you can write down small v in terms of summation net product v with vi, and vi I equal to 1 to n. So this is an interesting fact that you can always write it down by this fashion. Okay, so maybe you can obviously you can start giving some examples, and then we'll go to many applications and other corollaries of this Gram-Schmidt. Okay, apart from this corollary. Okay, so maybe you can start with some example that how do you actually write it down in terms of that. So okay, you can start with any vector space V. So let me just write it down, R3, and so what was that vector? So basis okay, so I think that we already discussed 1, 0, 1 and 0, 1, 1. And what was that vector? Orthogonal vectors. Okay, so you just do it again. Suppose this is the orthogonal vectors v1, v2, and v3. And with that example, you can find out that what will be the representation of any vector in terms of this orthogonal basis. This is, I think, we have discussed in last class. Okay, so you can write down v in terms of this v in abstract to v1 with v1 plus. So this one is orthonormal. Okay, orthonormal basis R3. Okay, and then v in a product of v2 into v2 plus v in a product of v3 into v3. Okay, so these are scalars, which are coefficients, and you can easily find out this. Okay, now so this is count out. So this is homework. We have discussed in last class how to find out these betas, and then you find out the coefficients of any vector v in terms of this given orthogonal basis. Okay, so one more identity which is coming from this is called, let's say, Parseval identity. I mean rather this is the inner product version of partial identity. It has obviously a general version for general nonlinear space other thing. Okay, what is the inner product version of partial identity tells you that. So suppose I am assuming that here again that is finite dimensional, and in that case what is happening. So let B is a finite dimensional inner product space. Okay, and yeah, so obviously that means you can have an orthonormal basis, and so you choose, and let's say B, say B1, B2, and Bn, B and orthonormal basis of B. Then what happens? Then if you choose any two vectors, okay, then for any two vectors, say let me write down, of course B1, B2 I have chosen, so maybe write down U and V belongs to V. So you can actually have inner product of UV, and that will be exactly equal to that. Okay, so I'm assuming that over complex numbers, field of complex number. Okay, yeah, and for real number it will be again trivial. Okay, so it will sum over 1 to n, and then this will be nothing but U with V1 norm, sorry, Vi, and then V with Vi's bar. Okay, and okay, so this is a general form, and then particular form also I will write down. This is identity for that's the inner product space. Okay, so the proof is not difficult, because once we have the Gram-Schmidt, we know that for any finite dimensional vector space you can always construct the orthonormal basis, right? But in finite dimensional vector space, the Gram-Schmidt method is not going to help you, because there will be a problem with converging issues, and then you need to uh, talk something called Fourier series. Okay, that is probably you will learn in maybe in your next course, say function analysis or something. Okay, so maybe I will just tell about briefly about what is Fourier series later, but let me give you a proof. So if B is finite dimensional and you have a basis B orthonormal, so you can write down your V. Yeah, so we can. Okay, so let me write down U first. I started with U, right? So you can be written as what? By the corollary we just discussed, that U Vi inner product with Vi I equal to 1 to n. Similarly, you can write down V in terms of summation I equal to 1 to n Vi, V inner product with Vi and Vi. Okay. So these are the representation of U and V in terms of these orthonormal basis vectors, and hence you can talk about the inner product with U and V. Now you see that this will be this sum, bigger sum I equal to 1 to n U Vi with Vi, and then sum over I equal to 1 to n EVI with VI. Okay, so now you use the property of inner product, and that tells you that this you can write down as summation u comma vi inner product, and the inner product with vi comma summation I equal to 1 to n v comma vi inner product with vi. Okay, so and obviously the sum is over I equal to 1 to n. Okay, now again you can apply the property of inner product. Now because this is in the second argument, the conjugate of this scalar will come outside, and then it will be nothing but okay. So yeah, so how to write down? So summation, or rather maybe I can write down as no, it's fine. So I think maybe from j, let me down j. This is dummy variable. Otherwise, there are too many i's are here. Yeah, so let me write down this j. There is no problem because I and j are dummy variables. Okay. So this is j. This is j. Okay. So now write down as I equal to 1 to n. The product u into vi, and then summation over j equal to 1 to n. Then you have v with vj bar, because this portion in the second component. Okay, and the inner product with vi vj. Okay. Yes, so now because your basis B is orthonormal, so it's in particular is orthogonal, right? So so this, whenever I and j are different, then vi vj will 0, right? The inner product of vi 0 becomes 0 this portion. This finally says if I not equal to j, it will only survive when I equal to j, and in that case that will be norm of vi square, right? But this is orthonormal, so the norm will be 1 always, right? So this becomes norm of 1. That will be 1, right? So when I equal to j, then only this sum survive, and then this product become v inner product v vi bar. Hence you can write down that in terms of, so you can write down as summation u vi I equal to 1 to n, and then v vi bar, and that is because of the property that when I not equal to j, the inner product vanishes, and when I equal to j, this is the norm square, and norm is 1, so this is 1. Okay, so this is a proof. Okay, now in particular if say u equal to v, then what happens? Then in the right hand side, left hand side will have inner product of u, and then in the right hand side you will have summation I equal to 1 to n u vi into u vi bar, right? But u is nothing but norm of u whole square, and right hand side you have I equal to 1 to n, and this is c, this is complex number, so z bar is nothing but mod of z square, right? So similarly this is mod of u vi whole square. Okay, and you can find out in many places this is as the Parseval identity. So there are many, this is a particular case, so some people also will say this is the Parseval yeah, so I wrote the general case because I am telling this is the identity, Okay, but some people also write down this is perceivable identity for inner product space. Okay. Okay, so this identity also has tremendous applications. You will understand few of those later. Now, yeah. So this is true. So this identity is for finite vector space. You can write down the exact forms, but for infinite vector space, because Gram-Schmidt method cannot gives you the exact like an orthogonal basis. So you cannot write down some equality. So you can have to write down something in convergent series in terms of Fourier coefficients. But I'm going to come there. Okay. Yeah. So before that, so let us give another um, example or rather another applications. Maybe in terms of theorem. Okay. Theorem. Or rather, you can say corollary also. So what is another example? Advantage of this finite dimensional inner space, that whenever you have a linear map or linear operator on finite vector space, you can easily very easily you can write down the matrix representation of the linear map in terms of orthogonal basis. Okay, and how this so let P be a finite dimensional inner product space. Obviously, I'm saying V inner product. Okay, so your basis. Say V1 to Vn, V and orthonormal basis of say V. V. Okay, so and also let you choose your linear map. T belongs to, so rather linear operator on V. Then what you can do? Then you can write down that matrix of T in terms of this basis B. Suppose this is matrix A. Then these ith row and jth columns are very easy. So what are those ith row and jth columns? They are actually nothing but inner product of T of so this is the opposite way. Aij will be T of Vj comma Vi. Okay, and this is obvious. Why? So the proof is so much obvious, because when you write down your vector Tvj in terms of linear combination of linear combination of this vector, you have these Aij's are there, right? Aij's. That is the matrix representation, right? So you write down the basis vector, image of basis vector in terms of summation Aij and Vi. Okay, I equal to 1 to n. But in this case, because you know that Vi's are the forms of orthogonal basis, then you know easily that this is obviously of the form Tvj with Vi and Vi. I equal to 1 to n, and that is coming from this for any vector V, can write down V comma inner product I with Vi and into Vi, right? So these are the coefficients are nothing but inner product V with Vi. Similarly here for Tvj it is Tvj comma Vi. So these are the actually these coefficients, because the representation is unique, right? With respect to this linear combination Vi, so this has to be this. Okay, so you can easily so you can enter the matrix and nothing but this the ith row and jth column will be inner product Vj with Vi's. So this will be your ith and jth column, the matrix. This is so simple to find out the matrix representation. Otherwise, in general, for a vector space where you don't have a inner product and in this finite dimension, you have to write down each image of each basis vector in terms of the basis vector and then do this, right? But yeah, it is very simple. Okay, so these coefficients are actually these coefficients of any vector in terms of the basis inner product operation. They have a nice name. They generally call this a Fourier coefficient. Okay, and that is after this famous French mathematician Jean-Baptiste Joseph Fourier. Okay. So what is that? What is the Fourier coefficient? So you start with, okay, so I am defining generally what is the Fourier coefficient generally people define. So let say we, so I am not assuming any finite or infinite here. So V inner product B and inner product space. So it may be finite, infinite, doesn't matter. Inner product space. Okay, and you choose a orthogonal subset. You don't know whether it is basis or not. So just I'm choosing and say be an orthonormal subset of V. So I have no idea whether it's finite or infinite. It can be anything. Okay. Then the Fourier coefficients of any vector. So you choose any vector of any small v, say belongs to V, is defined as this V with this element of this vector. So V is Vi's, where these Vi's are element of the orthonormal subset. Okay. So they are called Fourier coefficients. So for finding a vector space, because you have a orthogonal basis, then these coefficients are actually, we define this is Fourier coefficient. Actually, the coefficients of that is called, we define the Fourier coefficients. Okay. But in general, you can define it for any so okay. So this is called Fourier coefficients with respect to the basis or relative basis. So so how do I write? So this is basis relative to the basis. Rather, I should not say basis. To be rather I should say. Let me do this bigger. Okay, so so the concept of Fourier coefficient you can actually find out. I mean you can define any places. We don't need basis there, so you need only orthonormal subset. Okay, for that. And interesting thing is that this idea was more general, was found by this, as I told you, this Jean-Baptiste Joseph Fourier, who was a French mathematician. What was the idea? So he was actually trying to find out representation of periodic function. Periodic function means the function which takes same value after a interval, same interval times. So it coming back again and again. Okay, this kind of periodic functions. He wanted to find out the representation in terms of sine function, cosine functions, and so those was the idea, and you can see that these are the general case here, right? Okay, so that's why you call Fourier coefficients. But this Fourier series, everything you will learn later, much later in what is that? Maybe the course of functionalization other thing. Okay. But remember, for infinite vector space, for any vector, you find out the Fourier coefficient, Fourier series, but you cannot say that they are like equal. You say that kind of x is actually find dimension, and this is approximately or asymptotic to this some infinite say x vi and vi belongs to b. Okay, so if this sum is finite, then they converges obviously. Then they equal actually. If the sum is not finite, then the sum converges to x. So it's kind of that means you can make the difference between x and that is very small. Okay, in that sense. Okay. Okay. So now, so this was that. Obviously, some of the applications. Now, with the help of that, you can define. There is something called orthogonal complement. So let me say it. What is that? Orthogonal complement. Okay. Now, what is this? So you start with the vector space with the inner product. Okay. Or other inner product space. So how do I write down? So let be and I mean I am not saying in the finite dimensional whatever inner product space, and you have this you choose a subset rather non-empty, so S be a subset of B, define the orthogonal complement. Okay, orthogonal complement of S, complement of S in V obviously by these symbols. So this is we call S path. I will write down what is that. So this is we call S path, PRP. Okay. So what is this? This is collection of all such vector V in V such that the inner product with V with any vector in S, any vector for all vector rather I should say, this is 0 for all U belongs to S. Okay. So what does that mean? That means if you collect those vectors which are orthogonal to every vector of X, and this collection is called the perpendicular orthogonal complement of a given any given set. Okay, whatever is the set. Okay. Now it is simple observation. One can ask that what kind of set is this? For example, if you start with a set which is not a subspace, still S bar is a subspace actually. So S bar is always subspace. So this is a property you can check that the S bar is a subspace of V. How do you check that? Obviously, 0 belongs to S bar as 0 is orthogonal to any vector for all, right? Okay, and so this is simple. And then for subspace, what you need to check? You need to check that given any two vectors, okay, then sum will be again okay, and with the product, right? So if you choose any two vectors, say u1 and u2, say belongs to S bar, that is what? So that is u1 in a product with u equal to 0 for all u belongs to S, and also in a product of u2 with u equal to 0 for all u belongs to S, and then I have to show that inner product of u1 plus u2 equal to 0. But for any u belongs to this is true, because this is nothing but inner product of u1 with u plus inner product of u2 with u, right? And this is for all u belongs to S. Okay, and hence this is 0. So this is closed under addition, right? Similarly for multiplication also the same. So if say u belongs to S bar and some constant belongs to the underlying field F, then what you can do, then you can do or rather I say u1. Okay, so C u1 with u, this is nothing but C times u1 u, but because u1 belongs to S bar, so this quantity is 0 for all u belongs to S. Okay, so what does that mean? That means C1 is also element of S bar. Okay, so this is the proof that S bar is a subspace of V, right, for anything. Okay, so so given any subset, doesn't matter, the orthogonal complement is always a subspace. Okay, this is clear. Now an example, obviously, I mean, for any vector space, obviously you choose the trivial subspace and the part will be the full subspace. Similarly, part on the full subspace is a trivial subspace. This is obvious example. Now see, suppose you have R2, which is should be equal to say R2 over R. Okay, and then you choose so you choose how do I write down? So S, so S is space spanned by, or rather yeah, you choose singleton, doesn't matter. S is the vector 1 1 in R. Then what is S bar? So in S bar we will have all the vectors, say x1 x2 belongs to R2, such that inner product will be 0. What is the inner product? So inner product means such that inner product with s1 x2 with 1 1, this is 0, right? So what is the inner product here? So this is scalar product, right? So x1 into 1 plus x2 into 1, so this is x plus 1 plus, right? So that means x1 plus x2 equal to 0, so x1 equal to minus x2, right? So what does that mean? All the vectors such that it is of the form x comma minus x belongs to R2, right? What does that mean? That means this is the space spanned by 1 minus 1, this vector, or you can say minus 1 1, so both are the generator. Okay, clear? So this is subspace. Now one more property I must say here, that it doesn't matter if you choose the S bar and if you choose the part. So if you start with S and then go to S bar, or you first take the space spanned by S and then take the part, they are same actually. Okay, so S bar is same as the part of the space spanned by S, and so this is second property. The proof is simple, obviously. And this is just do this homework, you do it. Okay, this is simple. Okay, so you have to show that the subset of this and this subset of this. The one part is obvious because um, uh, so yeah, so which one is obvious? So if we start with any vector with this part, this contains all the vectors which is orthogonal to this, and hence this will be orthogonal to the source span by that only. Okay, so this is obvious, but this is also obvious. Both are obvious problems. Okay. Okay, so now another important observation I should say here that what happens. So this is defined for general space, but if you interpret final dimension in a product space, then what you can say about it? Okay, so um, so let us say we be a finite dimensional inner product space okay with so you start with a basis. Okay, whatever the basis doesn't matter. I don't want um, so okay, so with maybe I can choose space and the subspace obviously. Okay, so do I need final? Let me think about here. So if I choose any subspace and a basis, okay, so I don't need final answer there. Yes, it's true in general even. I don't need it. So you have a any inner product space and still this is to be inner product space and say W say you chose say subspace V such that it has a basis. Okay, such that be a basis W. Then to check some things in the W part, it is enough to check that they are orthogonal to the basis element, not everything. So then uh, say x belongs to W part if and only if x is orthogonal to the basis vector. What does that mean? That means um, this is actually I said here. Same thing I'm telling here. Okay, so with the basis. Okay, so if only x in a product of x with say v equal to 0 for all v belongs to the basis vector. Okay, then we have done. And the proof is also similar what I discussed before. So if obviously if this is true, then this is true because for any uh, any y belongs to W, because B is a basis of W, so you can write down y in terms of some finite sum of Ci Vi I equal to say 1 to k for finite sum. Okay, and this Vi is an element of B and Ci is at the this constant, right? And with the help of that, what you can do, you can when you take the inner product with x with y, then you see that this becomes 0 because x is in a inner product of x with all the vi's as 0, right? And hence y is also orthogonal to x. Okay, So what I am saying, so this is for any w. So x is orthogonal to y, and hence x is belongs to w part. Okay, so that tells you that x is element of w part. And conversely, if x belongs to w part, is orthogonal to every element of w, and hence is orthogonal to the basis element also. This converse part is also very simple, right? Okay, so these are the few properties of observation of this orthogonal complements. The question is that if we have a finite subspace, then can you kind of what should I say? Can you find out some kind of nearest vectors to any given vectors? Okay, and this method is going to actually help us to prove something called method of least square that we will discuss maybe in next class. Okay, but this is a very important idea, so I want to discuss this idea. So let me start with this theorem first. Theorem. So what does this theorem tells you that suppose you have a vector space V and a subspace which is finite dimensional. So let V be, and V can be infinite also. I have no problem in a product space. And I need a finite subspace, and W be a finite dimensional. This is important. You understand why. Finite dimensional subspace of V. Okay, so this is given to me, and then if you choose any vector y, then for any so you choose any vector. So let me write down, say y belongs to V. There exists unique, obviously this is very important, there exists unique vector u belongs to this subspace, and another vector z belongs to the orthogonal complement, such that your y is actually can be written as u plus z. It's so nice. So given any element, any vector of this vector space V, then you can write down this kind of a element, a component which is inside the finite dimensional space, and another component which is inside the orthogonal complement of that finite dimensional space, right? And obviously I will show you that there are like why this kind of U is important, and this is also unique. This is in the sense that you cannot find out any such other vectors. If we have, then they have to same. But we will prove it. Okay. So this theorem is one of the basic theorem that gives you the existence of vectors inside W which is nearest to Y. For any such Y, it's possible. Okay. Now, how do you prove this such theorem? So proof. So obviously as dimension W, let me write down dimension W. As this dimension of W is finite, so there exists an orthonormal basis. Okay, so I'm choosing the orthonormal basis. Okay, I know that this always exists binomial basis, right? Orthonormal, because I can do the Gram-Schmidt method. Orthonormal, the basis. Let me write down B, and the elements are say V1, V2, something say Vk of W. So this is the orthogonal basis of W. Okay. So now we will define our u. So what is my u? So my u is the so y is given. So you take the inner product of y with this basis vector vi. These are the coefficients of vi. So this is v of vi. I equal to 1 to k. Okay. And obviously k is the dimension of w because this is the basis, right? So you take the vector v u, which is this, and obviously that means that u is element of w, right? Because u is a linear combination of the basis vector of w. So I am claiming that this is the vector which is actually satisfying the condition in the given theorem. Okay. Why? Because so once this is there, then you choose your z is y minus u and check that, and so this is my z, and my claim is that this z is actually element of w part. Then I am done, right? Because if there is w part, then y can be written as u plus z, right? So this implies that y can be written as u plus z with u is element of w and z is element of w part. Then I am done. Okay, and not only that, I need to prove the uniqueness property also. But for let us prove this thing. Now, if you want to prove element z inside w pub, it is enough to prove that z is a orthogonal to all the basis vector. I just described that, right? So now, how to check that? What happened to z with this basis vector, say vi? Then you can write down your you know that your z is what? Z is nothing but y minus u, right? So we write down z is y minus u with vi's. But you also know that, so this is nothing but y minus vi's minus u comma vi's, right? But what is u? That you already know. So u you define as summation inner product of y with vi's. So let me write down j here, otherwise you will confuse. J equal to 1 to n and vj and the inner product with vi's, right? Now again you use the property of inner product that tells you that this inner product can be written as sum over j equal to 1 to n inner product y comma vj, and the inner product come inside, so vj comma vi, right? Now again when j equal to I, this will survive, otherwise this becomes 0 because this vi forms a orthonormal basis of my subspace w, right? So when I equal to j, this is 1. So in that case, you will have only this thing left with j equal to I, so it becomes y vi minus the same thing y vi, right? This is 0. So what does that mean? That means z is perpendicular orthogonal to all the vi, right? This is for true for all I equal to 1 to k, right? So z is orthogonal to all basis vector, and hence z is inside w part. Okay, so to prove something inside w part, you check that it is orthogonal to all the basis vectors. Then you are done. Okay, clear. Then how do you prove that this is actually a this is actually unique. So for uniqueness, so if you write down y in terms of say u plus z and some u1 plus z1, then what you can say? You can say that u minus u1 will be equal to z1 minus z, right? But you see that u minus u1 inside w and z minus z1 or other this vector is inside w part. So this is inside w intersection w part, right? Now, what are the only vector which is inside both the subspaces? This is only zero vector, right? There is no other choice, and hence u has to be equal to u1 and z has to be equal to z1, right? So that means that this representation is unique, and this u is called the orthogonal projection. So this u is called the orthogonal projection. Orthogonal projection of y on that subspace W. Okay, orthogonal projection. And not only that, this is actually more. So you can actually say that this is the nearest vector to y on W. How to say that? Okay, so let me write down that theorem also, or rather corollary, whatever. Okay, so so that whatever we discuss, so this is given to us u plus z, and then for any if you choose any vectors u1 belongs to W, what happened? The distance of u1 with, okay, so remember we define distance, the metric from x and y by this norm of u minus this. So this norm is at least the norm of y minus u. Okay, so this is the meaning of closest. So the distance from y with u is less than distance from y with u1 for any u1. Okay, and the proof is also simple, not very difficult. I will use something called this Pythagorean theorem that we already discussed. Okay, so how to use it? So now you see that this vector, so u minus u1, so this is also element of W, obviously, because u1 is element of W, u is element of W, this is element of W. But you see that this is also orthogonal to z. Z was orthogonal to u, but z was also orthogonal to this, because so this u minus u1 with z, this is actually u z minus u1 z, but u1 is orthogonal to W, so both is 0, right? So this is also orthogonal. So what does that mean? That means so so this is 0. So let me not write any more thing. So with z, this is 0, right? This is orthogonal to each other. Now come to the fact that the distance from y with u1, you can write down that in terms of or rather the norm of this, I should say. Let me write down the square of those norms, because I want to use Pythagorean theorems. So this is actually equal to u plus z minus u1, okay, because y equal to u plus z. Now you write down this is u minus u1 comma z, right? But see that these two vectors are orthogonal to each other. So Pythagorean theorems tells you that so you can write down separately this. So Python tells you that this norm is u minus u1 plus norm of z. Now this is using Pythagorean theorem, right? Okay, and obviously norm of any vector cannot be negative, so this quantity is always greater than equal to 0, and hence this is greater than equal to norm z, right? Whole square. But what is z? Z equal to, see, y equal to u plus z, so that means z equal to u minus y, right? So this is nothing but norm of y minus u. whole square, right? So what do we claim? That norm of any distance from u1 with y is always bigger than equal to distance from y with u, right? So u is kind of the closest vector to y on the subspace w. Okay, and this method we are going to use something called method inside method of least squares approximation method. Okay. Okay, so yes, so maybe okay, so okay, before maybe I will stop here and then we will discuss that other method later. Okay. Maybe okay. Maybe let me just discuss one more concept, and then we will go. So for finite vector space, as we said that there exists a orthonormal. So given any finite vector space or finite inverse space, so you can always extend any orthogonal or any linear independent set to a basis, orthogonal basis, right? And not only that, if you have a subspace, so for example, it's a W, say subspace, then you can talk about the W part or rather I should say, so maybe let me write down this. So I have given that dimension of V equal to finite, okay, and V within a product, some inner product, okay, this is given to us. And if W is a subspace of V, then you can obviously talk about W path, which also subspace of V. But interesting fact is that the dimension of V is actually sum of dimension of W plus dimension of W path. Okay. So this is very interesting fact that you can always write down some of these things. Okay. So for example, what you can do, so you write down. Okay, so you write down the basis B, as for example, V1, V2, Vk. So this is a basis of say W. Okay, and then you can always extend this basis to the basis of V. So you write down this V1 is V1, V2, Vk, and then Vk plus 1 to say Vn, which is a basis of V, that you can always say find out for finite vector space basis of V, right? Now the claim is that if you take the rest of the element Vk plus 1 to Vn, they forms W path. Okay, this is the claim. And so how do you claim? So okay, so maybe I should say orthogonal. Okay, so I should say orthogonal. Okay, so suppose you have a basis. Okay, so suppose you have orthogonal basis, orthogonal basis is orthonormal, then it is true. Otherwise not true. Orthonormal. Okay. Then you extend it to orthogonal basis of this using Gram-Schmidt method, and because orthogonal bases are also linear independent, right? So you can first you can extend these to a basis, and then the linear independence you can make it to orthonormal basis, right? So after that, suppose this is a orthonormal basis after all this process, orthonormal basis of B, then rest of these will be a orthonormal basis of W. So they will be such that this W part will be spanned by this B dash. Okay, and this I'm giving you a home exercise. You can easily find out this method. Okay, and you don't have to use anything. Only you have to prove the fact that these V1, Vk are perpendicular to V1, V2, Vk. And that is obvious because this bit inside V, they are actually orthonormal, right? So that's obvious thing. Okay, So with the help of this, I am going to stop here. Okay.